Hello, am I audible? I think I got disconnected. My internet was very poor. I had a very poor connection, internet connection. Now, am I audible? I got disconnected, right? Because everything stopped suddenly. I don't know. Okay. I think again it will start from the very beginning. Start. So, we are talking about today, we are talking about the kinematic theorem or the kinematic method of plastic analysis. Okay. So, this was your kinematic. Plastic analysis, right? So what does your kinematic theorem says that your internal work done is equal to your external work done. So what was your internal work done? You can denote it by W suffix I and W suffix E, the external work done. Now what was your internal? You have to know this, like what is your internal work done? Your internal work done is what? Your plastic movement into your rotation, right? So which is given by your plastic moment m suffix p into your rotation. Rotation I'll denote it by theta. Understand this to be theta. Okay, just give me a second, I have an important call. Okay, so your external work done was what? External work done equal to your force, or you can say the load, FORC, force into your deflection, right? So that is nothing but force is your P, into your deflection. Now your deflection, I have to mark it in this way. Your deflection, force into deflection, right? So Now, but you have to know what is your, this is your plastic moment for your internal work done. You have to know what is your plastic moment and your rotation. Okay, so if I give a star mark here, like where do we have plastic hinges? Okay, where we will form plastic hinges when plastic plastic hinge will form when where so you have to know plastic moment, you need to know the plastic moment. So where is your plastic moment, that you have to know, right? So for things to be in plastic hinge, where you will have your plastic hinge, you will have your plastic hinges as supports. For that, let me show you, let me draw a diagram for you all. Like I will take also a question. Suppose this is your question only. Also, okay, this is your fixed beam. Okay, this is your fixed beam. This is your fixed beam. This is your point load here. Okay. This is your fixed beam. You have a point load here, and suppose this point load is your P, given by P. This is your length, which is L. This is your length L. This is L by 2. Okay, sorry. This is your L by 2. That means your this load is at the center. So this is your L by 2, L by 2. Okay. So now this was your fixed. This is a fixed beam, right? Now you have to see, wait, where is your plastic hinges? Your plastic hinges are formed when you have at fixed supports. At fixed supports, you will have your plastic hinge will be formed. Okay, and also we are having under the point loads. Under the point loads, then you will have your plastic hinge at the point 0 shear in a span subjected to UDL of UDL. Okay, then we are having also, you will have a plastic hinge formed at a section where there is sudden change in the geometry. That is, that may be a I change, I section or something like that. Okay, so in the geometry. Okay, so your plastic hinge, where these are formed at fixed supports. That means here you will have your plastic hinges. That means if your plastic hinges are formed here, you will have a plastic moment here. Then you will have your plastic hinges are formed under this point load. Under this point load, then your plastic hinges are formed at the point of 0. Shear, this is shear. Okay, just correct this. This is shear. SHEAR, shear in a subject span subjected to a UDL. Then we have, when you have a plastic hinge, you will have a plastic hinge at a section sudden where you will have, suppose this is a beam, there is an extension here or here maybe, so the geometry changes, right? This is a plain straight geometry beam, but sometimes it may be a L shape or I shape, so then you are having a change in geometry, and that's why you will have a plastic hinge there. Okay, so what your kinematic theorem says? Your kinematic theorem says that your internal work done is equal to your external work done, which is your internal work done is the plastic moment into rotation, and your external work done is force into deflection. That means this force into deflection. Now, if we take this particular question, as your question, suppose find out the collapse load of this particular figure. This figure is given to you. Find out the collapse load here in this beam, which is fixed beam having a point load at the center. That's why your length as the span is L at a distance L by 2 from both the supports. Okay. Now at that now what you're going to do, you're going to use this kinematic theorem to find out the collapse load. So how you'll find out? For this you will have this is the span L, then we have here is the point load, so here deflection will be there due to this point load. See, this is your deflection, this is your angle rotation here, theta. This side also we can consider it to be theta angle. This is your deflection. This is your deflection. This is your point load here. That's why you have a deflection here. This delta deflection. So this was fixed. Both side. This is fixed. Fixed. Also, now you have here this is the theta angle, so this side also here will be theta, your angle will be theta. This is theta, this angle is theta, this angle is theta, this is theta, this is also theta. Okay, this angle is theta, this angle is theta, so therefore these two angles will be 2 theta. This plus this, here this angle is 2 theta. Okay, now we are asked to find out the collapse load of this particular figure. Now you know under the where you're okay, we have to find out the collapse load. Okay, so using kinematic theorem, we'll have what? We have to find out the internal work done and the external work done. So to find out your internal work done, what will be your internal work done here? We know that what? Our Wi Your Wi must be equal to We. Okay, so therefore for that what we have to do, we have to find out the internal one. Internal work done is what? Plastic movement into rotation. And where is your plastic movement? Where is your plastic moments? I told you this one, where your plastic hinges will be formed at fixed supports under the point load at zero shear in a plane such that when it is UDL, but here it is in this question we don't have a UDL. So and also at sections where there is change in geometry. So you see here this is fixed. So we will have a plastic hinge here, here fixed supports and under the point load. So that means at this deflection also we are having our plastic hinge. So plastic moment will be the how many moments? 3. So what will be our internal work done? Our internal work done will be this one, MP into theta. So for this particular point A, suppose this is A, so what will be here? The MP, okay wait, I will use this bracket, MP into theta. I am denoting this theta by this at the rate symbol. Then plus we are having here one plastic moment will be there. So again one more MP into theta. Okay, sorry, theta. Now here this is your MP, but what is the rotation or the angle formed here? This one, these angles are formed here at this point. So that is theta plus theta, twice theta. So 2 theta. Okay, theta, this theta plus this theta, twice theta. Now we are having again, this is a plastic hinges occurring here. So what will happen? Plastic moment is this. So MP into, we are having again this angle, it has a rotation of theta, this one. So we got what will be our Wi, which is our internal work done. This is MP theta plus symbol 1 MP theta, 2 MP theta plus again one more 2, 3, 4, 4 MP theta. So 4 MP theta is our internal work done. Now what will be our external work done? Our external work done is given by P into deflection, right? So our load is how much? Force or the load, it is P into deflection, P into deflection, right? So what is our deflection? P into deflection. Now to find out this deflection, what you have to do, we will consider this triangle. We can consider this triangle. Now if we consider this triangle, if we are considering this triangle, this is the triangle we have. This is how much? This is L by 2. L by 2. We are having here, this is delta, this is theta. This angle is your theta and this is your delta. Now from when we use this triangle, when we are taking this triangle, what we can do is we will get how much? Tan theta. From here what we'll get? Tan theta is equal to how much? Tan theta will be delta by L by 2, right? Tan theta, perfectly blue. So delta, here delta again I have to mention it here. Delta by L by 2. L by 2. So that means what? Your theta, tan theta, it is very, very small. We are considering theta to be very, very small. So our theta, wait 1 minute. Okay. So our theta is how much? This is your theta which we are considering to be very, very, very small, and therefore this tan theta is equal to theta. So theta is equal to how much? This angle theta is equal to delta by L by 2. So from here, when we have delta, theta is equal to delta by L by 2, we can find out this delta, which is this. We need to calculate what is our delta. So from this, we will get our delta. Delta will be how much? Theta into L by 2. So our WE, the external load, will be P into theta into L by 2. Okay, P into theta into L by 2, right? So now we know we have calculated our internal and the external work done. Now if we can use our kinematic theorem, which is internal work done is equal to external work done. So using kinematic theorem, what will have? Your internal work done is equal to external work done. That means your 4, I'll write in shortcut, 4 mp theta is equal to our, that means P theta into L by 2, right? So from here, you will theta cancel, these two thetas are cancelled. So from here we can find out our this one. That means what will be our MP? What we have to find out? We have to find out the collapse load. Here in this question we are asked to find out the collapse load, right? Find the collapse load. Find the collapse load for this now. So now if you see from here, you know 4 MP is equal to P into L by 2. So what will be your P now? Your P you can find out from here. Your P is coming to be, your capital P, which is your collapse load, is coming to be how much? 4 to 8. 8 megapixel. Sorry, megapixel, what I'm telling. P is equal to 8 MP, which is your plastic moment, divide by capital L. This one 4 to the 8 MP by L, which is your collapse load. So in this way we can calculate our collapse load with the help of using what? Using our kinematic theorem. Okay, using this kinematic theorem. Done? Fine. Hello, am I audible? Okay, so understood this thing. You have to use this kinematic theorem to find out the collapse load. Using this you can find out your collapse load. So you can take a screenshot here or you can take a snap. I think I'll also, okay, kinematic. Okay, so because now if I go to the next question, then I think these annotations will get vanished. So if you take a screenshot or note it down, whatever is here. Okay, so next we will do a problem. This was a simple question where we have a fixed support on both the ends and we have a point load at the center, right? So Now if you have a question where you have a fixed, okay, I'll see if you can done this one. Shall I remove these annotations now? Shall I remove? Okay, so okay, now if I give you a question here, this is your beam, it is fixed on this side, you have a point load here at the center as usual. Wait, let me remove this. You have a point load at the center. Now this is your L, the span is again, it is given by L because it is at the center, so this is your L, this is your capital L, this is L by 2, L by 2, L by 2, and this is your P, capital P, which is the load. Okay, we have, this is your, okay, this is your fixed here, and this side it is hinged. This is hinged on this side. Okay, meeting is going to over. Meeting is going to end, right? So what to do? Will we have a class at 1 p.m. and the attendance, I have not taken your attendance now because I'll be taking the same attendance at this 1 p.m. class. Okay. For both the classes for now, and then at 1 p.m. we are going to take the class there. In that class I'll take both the attendance, I'll give it together. Okay, now so this is going to get removed. I think simply I have done. So I have given you this question right now. So what you do, you try to solve this question now. You find out the, calculate the collapse load. Try to find out the collapse load. The same thing you have to, this is the beam given to you which is fixed at one end and hinged, and you know what is your how you can calculate your collapse load by using the kinematic theorem, which says that internal work done is equal to the external work done. And so your internal work done is how much? Your internal work done is your plastic moment into your rotation, you know that. So you try that plastic moment where at this point, at this, in this figure you will have your reflected diagram figure here, and then how much is your internal work done, you will know. Where is your MP, the plastic moment, where it is occurring, you will know, because it occurs at the fixed point, fixed support, and under the point loads. This is hinged, okay, remember this is not fixed. Okay, so try to find out the collapse load, equate both the plastic internal and the external work done, and if you can, you try. Otherwise in the next class we are again going to also solve this sums, solve this problem. Okay, what happened? Okay, and this is the video which is uploaded now, which is being recorded, I think because in the ERP it is DOS class, it is mentioned there, I'll upload this video only there, okay? Because analysis, I think it is not there for uploading this video again. With your attendance and that video, I'll upload there. Okay, then I think we'll remove the class. I'll stop sharing now. And I may be late also little. By 1:15 we'll meet again. Thank you. We'll continue in the next class.
Thank you, ma'am.